Okay, let's try the H2 molecule using the Lewis symbol. We have this kind of complicated picture showing us, well, the reason why it happens is because this is the lowest energy configuration for this collection of protons and electrons. Okay, and that's sort of complicated, but there's easier ways using Lewis symbols to make what we call Lewis structures to predict, you know, the type and number of covalent bonds that exist in these molecules, covalent compounds. So for hydrogen, of course, if we use the Lewis symbol, it's just, you know, there's one atom and here's another atom of hydrogen. What's going to happen is they're going to come together in space, and those two electrons, okay, they're going to come together in space. You're going to end up with these two electrons near each other between these two atoms, okay? And so a covalent bond is a shared pair of electrons. This pair of electrons, these two electrons, are shared between these two hydrogen atoms, all right? And another way to draw this is like this. So we use these little dashes between elemental symbols to indicate shared pair of electron. Okay, so this very important to know that this little dash means something. It's a chemical bond. It's a particular type of chemical bond. It's a covalent bond indicating a shared pair of electrons. Okay. Now you can do the same thing. Try an HF molecule. You start with just the Lewis symbols for each individual element. So hydrogen, and then fluorine. Sorry, my bad. Has 1, 2, 3, 4, 5, 6, 7. So individually, you can see the fluorine has 7, the hydrogen has 1. You know that the hydrogen would really like to achieve what we call a satisfied valence shell. That's why it moves to a lower energy here. It's just energetically more favorable for the hydrogen to have 2 electrons in its valence shell than to have 1. So you see it's higher energy when it's by itself. It moves to a lower energy state when it's together. And for hydrogen, that happens to be 2 in the valence shell. Fluorine, of course, and it's only hydrogen and helium, and there's a couple other exceptions that we'll get to when we need to, but hydrogen and helium need 2. Fluorine, like most other elements, needs to have 8 electrons in its valence shell. So what's going to happen is these two atoms are going to come close together in space, and the electrons, the one electron from the hydrogen and the one other electron from the helium, are going to occupy a space between the two, and together collectively this molecule is going to be in a lower energy state than this atom by itself or this atom by itself, and so it's going to stick together. And so I can draw it like this. And again, of course, this dash is just modeling this shared pair of electrons. That's a covalent bond. I can leave it like this, and that's telling me on this fluorine, I have 1 shared pair of electrons, and I have 2, 4, 6 unshared pairs of electrons, or excuse me, 6 unpaired electrons, or 3 pairs of unshared electrons. Sometimes they're called non-bonding pairs. It can be called a non-bonding pair because it's not involved in bonding, or an unshared. It means the same thing. Non-bonding or unshared pair of electrons. And there's 3 of those pairs. All right. And so what you have to visualize then is that this hydrogen, of course, this is the sphere of the atom. It's got 2 electrons here. And then this fluorine, this is the sphere of the fluorine. It's got 2, 4, 6, 8 in its valence. So that's how we can say that this is now full and this is full, because they're sharing these 2. So when I count individually, oh yeah, hydrogen has 2. And then I can count and look at the fluorine individually and see, yeah, the fluorine has 8. All right, and so when I draw it this way, it's the exact same thing as this. I can draw it this way and still see and think this, or I can even draw it this way. I'm not showing the non-bonding pairs of electrons or the unshared pairs of electrons, but I know from my chemical intuition that this is the exact same thing as this, is the exact same thing as this. So when you see this and you model this, when you write it like this, HF, this hydrogen fluoride, you should be thinking this, all right? It's a deeper understanding of what's physically going on with this particular little molecule.